PVC polyvinyl chloride is made by a free radical chain reaction that looks a lot like a row of falling dominoes. The monomer is vinyl chloride, CH2 equals CH chlorine. Initiation. A small amount of an initiator, for example benzoyl peroxide, decomposes to give two radicals R dot. Each radical attacks the double bond of a vinyl chloride molecule, breaking the pi bond and forming a new carbon-centered radical, CH2CH chlorine. Propagation. The new radical immediately grabs another vinyl chloride molecule, extending the chain by one repeat unit and leaving another radical at the chain end. This step repeats many times, adding thousands of CH2CH chlorine units, just like each falling domino knocks over the next one. Termination. Two chain radicals meet and combine, or a radical abstracts a hydrogen atom from another molecule, ending the growth. The overall reaction can be written as NCH2 equals CH chlorine yields a polymer chain of CH2CH chlorine repeated n times. The process is called addition polymerization because the monomer adds across the growing chain without losing any atoms. The chlorine stays attached to every second carbon. In industry, PVC is not made in a beaker, but in large reactors that keep the reaction safe and uniform. Two common reactor designs are suspension or bulk reactors and loop reactors. Initiators, usually organic peroxides, for example dicamyl peroxide, or azo compounds, for example azabisosobutyronitrile, IBN. They decompose at 40 to 80 degrees Celsius to give radicals. Reactor type. In a suspension reactor, the vinyl chloride gas is bubbled into water containing a suspending agent, for example polyvinyl alcohol. The polymer forms as fine beads, which are easy to filter and dry. In a loop reactor, the monomer initiator mixture circulates through a heated loop, allowing continuous removal of heat and better control of molecular weight. Typical conditions. Temperature, 40 to 80 degrees Celsius. Higher temperature speeds initiation but also increases side reactions. Pressure 1 to 5 atmospheres. The monomer is kept as a gas or saturated liquid. Inert atmosphere, nitrogen or argon to avoid unwanted oxidation. Reaction time 1 to 3 hours for batch, continuous for loop reactors. Catalyst concentration, 0.01 to 0.5 weight% based on monomer. The combination of temperature, initiator dose, and reactor design lets manufacturers tune the degree of polymerization, DP, and therefore the strength, clarity, and flexibility of the final PVC product. Explanation. The degree of polymerization, DP, tells how many repeat units are linked together in one polymer chain. It is related to the number average molecular weight, m sub n, by the simple equation. M sub n equals dp times m sub 0, where m sub 0 is the molecular weight of the monomer. Vinyl chloride equals 62.5 grams per mole. Example, suppose a PVC batch is stopped when the conversion is 85%, and the measured m sub n from gel permeation chromatography is 31,250 grams per mole. 1. Calculate dp. dp equals m sub n divided by m sub 0 equals 31,250 grams per mole, divided by 62.5 grams per mole equals 500. 2. If you want to predict m sub n for a lower conversion, say 60%, assume dp is proportional to conversion. dp sub 60% equals dp sub 80 5% times 0.6 divided by 0.8, 5 equals 500 times 0.706, approximately 353. M sub n sub 60% equals 353 times 62.5, approximately 22,060 grams per mole. This simple proportionality works for free radical polymerization when chain transfer and termination rates are relatively constant. Engineers use the relationship to target a specific molecular weight range that gives the desired balance of stiffness and processability. PVC shows a unique mix of physical and chemical traits because each repeat unit carries a chlorine atom. Below about 100 degrees Celsius PVC is stable, but at higher temperatures it begins to dehydrochlorinate, losing HCl and forming conjugated double bonds. The material turns brown and becomes brittle. The reaction can be slowed by adding heat stabilizers such as calcium zinc or organotin compounds. Tensile strength typically 35 to 55 megapascals. Elongation at break 30 to 100% for soft PVC or less than 10% for rigid PVC. The chlorine makes the chains stiffer, so rigid PVC is hard and impact resistant. The chlorine envelope repels many acids, bases, and organic solvents, so PVC does not swell in water, dilute alkalis, or most hydrocarbons. The chlorine releases HCl when heated, which quenches flame radicals. PVC is self-extinguishing without added flame retardants. PVC's dense structure prevents water and gases from passing through, making it ideal for pipes and films. These properties together explain why PVC can replace metal in corrosive environments, while remaining lightweight and inexpensive. Explanation: when you look at an engineering exam, the key selling points of PVC are easy to remember with the mnemonic CRISP. C stands for corrosion resistance, no rust, survives acids and salts. R stands for robust mechanical strength, good tensile and impact values. I stands for insulation, excellent electrical dielectric constant used for cable sheathing. S stands for simplicity of processing, can be extruded, injection molded, or calendared at 150 to 180 degrees Celsius. P stands for price advantage, one of the cheapest polymers per kilogram. Major applications with real-world analogies. Number 1, water distribution pipes. Like a garden hose that never gets a hole, PVC carries water without leaking or rusting. Number 2, window frames and roofing sheets. Think of a plastic window pane that is strong, UV stabilized, and cheap compared with aluminum. Number 3, cable insulation. The jacket around electrical wires is similar to a protective coat that keeps the electric current dry. Number 4, medical tubing. Because it does not react with body fluids, PVC tubes act like a harmless straw for fluids. Number 5, flooring and wall cladding. Rigid PVC tiles are like sturdy Lego pieces that lock together and resist stains. Comparative advantages over metals. Lighter weight, about 1/5 of steel, no corrosion, lower maintenance, and easier to shape into complex profiles. Over other polymers, for example polyethylene. Higher stiffness, better fire performance, and superior chemical resistance to chlorinated solvents. Exam type answer often. PVC is a thermoplastic polymer obtained by free radical addition of vinyl chloride. Its chlorine atoms give it fire retardancy, chemical resistance, and a high modulus, which make it the material of choice for pipes, window frames, and cable insulation, especially where cost and durability are critical. Bakelite is the first widely used thermosetting plastic, and it is made by a condensation step growth polymerization between phenol, C6H5OH, and formaldehyde, CH2O. The reaction proceeds in 2 stages. 1. Methylylation phenol reacts with formaldehyde under acidic or basic conditions to give hydroxymethyl phenol, C6H4OHCH2OH. This step adds a CH2OH group to the aromatic ring. 2. Condensation. The hydroxymethyl groups on 2 phenol molecules combine, releasing a molecule of water and forming a methylene bridge, CH2, between the rings. Repeating this step builds a 3-dimensional network of phenyl rings linked by CH2 bridges. The overall simplified equation is N times C6H5OH plus N times CH2 yields, under acid/base, C6H4CH2 sub N plus N times H2O. Because each step eliminates water, the reaction is called condensation polymerization. Once the network becomes large enough, the material hardens irreversibly. It cannot be remelted, which is why Bakelite is called a thermoset. In everyday life, it appears as the hard black case of old radios, electrical switch plates, and the handles of kitchen utensils. The process can be carried out in bulk, in a solvent-free melt, or in a solvent-based system where the polymer forms as a solid precipitate. The choice of catalyst, usually hydrochloric acid for Rizal or aniline for Novolac, and the temperature 120 to 180 degrees Celsius determine whether the final polymer is a self-curing Rizal or needs a hardener Novolac. Bakelite can be prepared in 2 main ways, giving 2 distinct families of phenol formaldehyde resins. Rizal or condensed resin, the reaction uses excess formaldehyde to phenol ratio greater than 1. Under acidic conditions, the mixture proceeds beyond the methylated stage and begins to cross-link while still in the liquid state. The resin is thermosetting by itself. When heated approximately 150 to 180 degrees Celsius, it auto-cures to a hard solid. Typical conditions: formaldehyde to phenol molar ratio equals 1.2 to 1.5. Catalyst half to 1 weight % hydrochloric acid or zinc chloride. Temperature 90 to 120 degrees Celsius for the reaction, then 150 to 180 degrees Celsius for curing. Novolac or non-condensed resin, here excess phenol is used, ratio less than 1. The mixture stops at the methylated stage, giving a low molecular weight prepolymer that is thermoplastic until a hardener, often a hexamethylnitretramine, HMTA, or urea, is added. The hardener provides additional methylol groups, allowing the network to cross-link on heating. Phenol to formaldehyde molar ratio equals 1.5 to 2.0. Catalyst 0.1 to 0.5 weight % acid, often oxalic acid. Reaction temperature 80 to 100 degrees Celsius, curing with hardener at 150 to 170 degrees Celsius. The key difference is the molar ratio and the need for an external hardener. Rizal is self-curing, no extra agent, making it suitable for molded parts that must set quickly, while Novolac offers better control of viscosity and is used where a long pot life is needed, for example laminated boards, electrical insulation sheets. Explanation: the stoichiometry of phenol formaldehyde condensation is crucial because it decides whether the resin will be a Rizal or Novolac and what the final network density will be. The phenol formaldehyde molar ratio, R, is defined as R equals N phenol divided by N formaldehyde. For a Rizal, we want R less than 1, excess formaldehyde. For a Novolac, we want R greater than 1, excess phenol. Numerical example: suppose you need 0.5 moles of phenol formaldehyde resin with a target degree of polymerization dP of 10, and you decide to prepare a Rizal. Step 1. Choose a formaldehyde to phenol ratio of 1.3, typical for Rizal. N formaldehyde divided by N phenol equals 1.3. Step 2. Let NP equal number of moles of phenol, then N formaldehyde equals 1.3 times N phenol. Step 3. The total moles of monomer units, phenol plus formaldehyde, that will become part of the network are N total equals N phenol plus N formaldehyde equals N phenol times 1 plus 1.3 equals 2.3 N phenol. Step 4. We need N total equals 0.5 moles, so 2.3 N phenol equals 0.5 implies N phenol equals 0.5 divided by 2.3, approximately 0.217 moles. Step 5 then. N formaldehyde equals 1.3 times 0.217, approximately 0.282 moles. Thus, to obtain 0.5 moles of Rizal resin you would weigh phenol 0.217 moles times 94.11 grams per mole, approximately 20.4 grams. Formaldehyde as 37% aqueous solution, M approximately 30 grams per mole. 0.282 moles times 30 grams per mole, approximately 8.5 grams of pure formaldehyde, which corresponds to approximately 23 grams of 37% solution. If instead a Novolac is required with R equals 1.6, the same calculation would give a larger phenol amount and less formaldehyde, illustrating how the ratio directly controls the network's cross-link density. Remember, R less than 1 yields Rizal self-curing. R greater than 1 yields Novolac needs hardener. The closer R is to 1, the more balanced the network, giving intermediate hardness and heat resistance. 1. Compare the polymerization mechanisms. PVC free radical addition of vinyl chloride, a chain growth process where each monomer adds without loss of atoms. Bakelite condensation step growth polymerization of phenol with formaldehyde. Each step eliminates a small molecule water and builds a three-dimensional network. 2. How do the structures differ? PVC linear chain repeat unit CH2CHCl. Chlorine atoms are pendant, giving the polymer a polar character, but keeping the chain flexible. Bakelite: highly cross-linked aromatic network. Phenyl rings linked by methylene CH2 bridges. No linear chains remain after cure. 3. What are the key thermal properties? PVC: starts to dehydrochlorinate above 100 degrees Celsius. Needs stabilizers. Melt processable thermoplastic. Bakelite: once cured, it cannot be remelted. Thermoset. Stable up to 200 to 250 degrees Celsius. Does not emit HCl on heating. 4. Discuss mechanical strength and durability. PVC: good tensile strength 35 to 55 megapascals and impact resistance. Flexible in the plasticized form, rigid when unplasticized. Bakelite: very hard, brittle, high compressive strength, excellent dimensional stability, poor impact resistance. 5. Give 2 major engineering applications for each and why they are chosen. PVC: water pipes corrosion-free, cable insulation dielectric and flame retardant, window frames light cheap. Bakelite: electrical switch housings and sockets, high dielectric strength heat resistance. Automotive brake pads and gear casings abrasion resistance. 6. How does the synthesis route affect processing cost? PVC: bulk or suspension polymerization in large reactors, inexpensive initiators, can be continuously produced, low unit cost. Bakelite: requires careful control of formaldehyde-phenol ratio, acid-base catalysts and occurring step. Batch-wise production higher cost, but the end product heat resistance justifies it for specialty uses. 7. Summarize the environmental considerations. PVC: generates HCl and dioxins on high-temperature incineration. Chlorine content raises disposal concerns. Bakelite: formaldehyde is toxic, however the cured product is inert and does not release volatiles. PVC is a thermoplastic obtained by free radical addition of vinyl chloride. Its linear chlorine-substituted chain gives it flexibility, good mechanical strength, and intrinsic flame retardancy, making it ideal for pipes and cable insulation. Bakelite, in contrast, is a thermoset phenol formaldehyde resin formed by condensation polymerization. The highly cross-linked aromatic network provides high heat resistance and electrical insulation suitable for switchgear and heat-exposed components. The two polymers differ fundamentally in synthesis: chain growth versus step growth, processing melt processable versus cure only, and end-use performance, which is the focus of many engineering chemistry exam questions.